Today is the second lecture for stability versus efficiency. So let me just quickly go through what we discussed yesterday. So we mostly discussed about a cooperative game, or simply in short we say it's a TU games. So what is a TU game? So we have two components, N and V. N is the player set or set of agents, and we define a function on set of all possible coalitions. It's a real value function with the restriction is that the empty coalition always the word for the empty coalition is 0, right? So once the game is coalitions are formed, the game is defined. So then we have the solutions or allocations for the cooperative game. Let's Gn be the set of all cooperative games on N, right? So then a solution is another function on this set of N. N is the cardinality of the player set, right? So such that it satisfies the efficiency conditions. So what is the efficiency condition? Do you remember that? That we allocate the worth of the gain coalition among the player. Right? Then we talked about some popular allocation. So first allocation, the safely value. Right? Do you remember how it's defined? So it's defined on marginal contribution of a player. So a particular player I, the safely value for the game and V, it's actually what? Summation overall S is a subset of N minus I. Cardinality of the coalition S factorial, N is the cardinality for N, minus S minus 1 factorial divided by N factorial, and over all marginal contribution for the all player for all coalition of the player I. So this is how the safely value is defined. No, Banjab is different. The coefficient for Banjab is what? 1 by 2 to 1 divided by 2 to the power n minus 1, right?
But here S minus is minus
n. Yeah. So another way, these two are equivalent. If S is a subset of N such that I in S, so then it will be S minus 1 factorial, N minus S, and divided by N factorial. So yeah. So I think yesterday I mentioned this one, the another one, right? Okay. And what are the axioms which satisfy the set of axioms that satisfy by safely? First is obviously efficiency, this property, plus symmetry. What is the symmetry? So if the two different players, their contribution is same in this game, then they will safely will give them the same allocation. Anonymity almost same. It's more a strong condition, anonymity. So what is anonymity? Okay. So what is the difference? So let me tell you what is the difference between symmetry and anonymity. So symmetry means actually if there are two players, different player, they are not equal, and their contribution is same in that game, right? Then the safely coefficient for the player I and for the player J will be same. So from the expression itself, you can prove it. Okay. So now, what is the anonymity? Anonymity is be the stronger condition. So anonymity is what we have to. So for players set N, so first we consider a permutation of N. Do you know what is a permutation? So we consider one permutation. So how many permutation we can have for players set N? n factorial, right? So we consider one permutation, obviously this equal to n, right? And then we define another game. First we take a one permutation among all n factorial, then we define another game, permuted game on this. So let's take an example. So one simple example, right, for the 3-player game. If I consider a one permutation, say like this, so permutation of 1 is 2, 2 is 3, right? So let's consider this permutation. So now I can define another permuted game on this permutation, such how it will be right. So here it will be like what? Say, so definitely v of pi v, and in this case it will be v of n, but say permutation of 1 and 2, it will be what? So what is the permutation for 1 and 2? 2, 3. So it will be v of 2 and 3. Like that, we define the game. So now, what would be the Shapley allocation here? In this case, the Shapley allocation for the pi 1 in this game equal to the Shapley value 1, right? This is actually 2. So we consider the permutation, the 1 pi of 1 is 2, and we define the game this way, and then when we, so now we have a Shapley allocation, right? So whatever the player is getting in game V, after the permutation we have another game pi V. So whatever the player will get in that pi V game, the player 2, that pi 1, it's same. So it's actually what? We are just changing or the levels of the player, right? We have just a different level. The players, when we change the level of the player, but they will get according to their contribution. Okay. So this is the only difference between symmetry and anonymity. So anonymity is a more generalized concept, right? So in case of symmetry, we just consider 2 player, but in case of anonymity, we consider for all player, right? Okay. So next, so efficiency, anonymity or symmetry, then another we have linearity and another null player, right? What is a null player? If the player contribution is almost 0, then he will give, Shapley will give him 0 allocation. So means just a particular player I, his contribution whenever in that coalition or not, the what is always 0 or same, right? Okay. So next, what we discuss? We discuss equal division, right? Equal division is, or egalitarian is simply we equally distribute the worth of gain coalition among the players, right? And what are the axioms? Its characterization is almost similar to the Shapley, only the difference is that it satisfies nullifying player. Do you remember what is the nullifying player? It's almost similar to null player, right? All whenever he is in that coalition, the worth is always 0, right? So then we talk about the core solution, right? Do you remember how we define the core solution?
Individual sum is equal to v of n,
And that
for each subset
for its coalitions, it should be overall summation for that allocation should be greater than whatever the worth of that coalitions, right? So it will be a for all yeah, it is xi, I in S is greater than equal to V of S. For all S is a subset this strictly, right? First condition, if we can consider is equal also, yeah, or we can consider is less than also. Both we can consider. Yeah. Here equal symbol is there, right? Yeah. Yeah, but it will be more restricted then. You won't have that. It is efficient, yes. So okay. So you are saying that if you put here the equal and you, again here equal. So second condition you want to put the equal. For some it is equal, or for some I s it is equal, not for all. Yes. No, this is correct, right? And you were saying that for s, so you want to put that equal sign here or?
No, for all S, it's a proper subset, right?
Yeah, proper subset, right?
Instead of proper, you just take any subset, like including N itself.
Including n itself, no, in earlier conditions, okay, in earlier condition I was written like this. So for all n, I mean for that only the GAN coalitions, we consider it is. And for any, when S is not n, then we consider it is greater than equal.
Now,
Yeah.
what he's saying is for all S, it can be like just subset, not necessarily proper.
Okay, okay, any subset. This is what you are saying.
Yeah, now
Okay.
when both poles it's actually equal, so less than or equal to and greater than
Hmm.
we have some calculation.
Okay. 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 Okay, then next we discuss that. So sometimes, so we have an example where we show that separately or equal division is always exist, always unique. But in some cases we have a non-empty core, right? Or some cases we have an empty core. So we have an example where that core was empty, and so there is a theorem. The theorem says that if the game is convex, then core is non-empty. Okay. So what is a convex game?
Worth of A union B is less than equal to worth of A plus worth of B minus.
It's greater than. Yeah. So whatever they, so suppose S and T are two subset of N, two coalitions, and whatever, if they join together, then their worth should be greater than where whatever they are generating individually, and the minus of the player, the worth, the worth of that coalition of the player who are common in both S and T, right? And moreover, the safely value for this always belongs to core. Not only simply value, there are some other value also belongs to core if the V is a convex game. So other value that I don't want to discuss because some values are not extended to introduce in network games, but this kind of value already introduced for network games. Okay, so then we talked about Banjab value. So Banjab value is actually a power index. Why we call it a power index? Because it does not satisfy the efficiency condition. Okay, and we talk about that voting game or simple game. Do you remember how we defined a simple game?
Everyone has W votes and
Yeah, some weights.
control Q.
Uh-huh.
If the sum of all the votes
If as is 1 is winning coalition or 0 otherwise. It's not a winning coalition. So how we define a winning coalition? So suppose each player has a some votes right. Okay. So they associate each player has a some weights or we can say some votes and is greater than Q. Q is the code that is necessary to pass the bill or anything, right? So this is how a voting game is defined. And then the power index, some power index are introduced for these special kind of games. So one is called the Banjab value. That Banjab value is defined as so it consider all the marginal distribution of a particular player I and it's simply divided by 2 to the power n minus 1, right? Okay. So apart from efficiency, Banjab value satisfy the other conditions of the Shapley axioms, like including linearity, anonymity, and null player. So it has another axiom. It's called total power. So that is totally technical. What is the total power? Actually, total sum of Banjab value for the player is actually what? It will be 2 to the power n minus 1. Is actually so numbers of player in S, I guess, right? And minus numbers of players in n minus S. It is something like that, right? So when you sum overall, you will have this kind of expression. So probably this expression might not true. I am not sure. Okay. Okay. So apart from we have all discussed all of them, right? So apart from, did we discuss anything? No, I guess. Okay. Okay, then today we are going to talk about the second part, communication situation or network games. So, okay. So let me tell you what is a communication situation first. So first Meyerson introduced this idea of the communication situation for any say network game. So I have one network game here, two games, right? So what Meyerson actually did, so he tried to analyze the cooperation structure. As I said, for any cooperative game, that any group of players try to cooperate with one another. They have some binding agreement and they make coalitions, right? They make coalition. So Mayashan try to understand how this coalition is formed. So he used a graph theoretic idea to understand this cooperation structure in these coalitions in a TU games. Okay, so for a player set N, if we try to think about the network structure among the players in N, so how many possible graphs are there? 2 to the power 2 to the power NC2, right? Or we can remove the empty graph also. So it will be -1, right? Okay. So what Mayashan did actually, he said, so his basic assumption was that the player can, when we have a player set, coalition S, they can generate a word only when they are connected somewhere, somehow. Okay. So if I have a player set N, say 1, 2, 3, 4, 4-player game, suppose that the coalition 1, 2, 3 will be formed only when they are connected somewhere, somehow. So if I say they could be connected this way, or there can be another link between 1 and 3, right? This is a one possible way. Okay. So the coalition S can generate a word only when they are connected somehow in a network structure. There must be a network structure among them. So then only they can generate some word. Okay. So for N particular TU game N, so we have this much of graph structure. So for each particular graph, this tuple he considers as a communication situation, right? So for a only single particular TU game, so we have a 2 to the power n into n minus 1 numbers of, for a particular n, so we have this numbers of graph, right? So for each graph we can have one communication situation. Okay. So then under the graph Z, each coalition, so I am going to define this notation S over Z. Okay. For any coalition S or any graph Z, right, any graph Z is actually what it divided the coalition S into some partition, right. Say in the previous example, say I was saying that when for the 4-player game S is 1, 2, 3, right. So we have we can have a different graph structure, right. Say we can have complete graph among these 3 players. We can have, there is only 2 link, there is no one link like that, and we can have the isolated player also, right, or they can be empty, right. So if we consider any of them, any graph over S over Z, so for this graph, right, so we have, it will be like whole coalition, whole coalition S, But if we consider this kind of graph, it will be again the whole coalition S. But if we consider this, for this graph, so our coalition S will be a, so it actually will have a partition of S. So that partition, say if I label it 1, 2, 3, it will be like 1, 2 and 3. Okay. So it depends on the graph structure, which structure we are going to consider. So it always divided the whole part. I mean, it's divided the, it makes the coalitions into a partitions, right? So whenever we consider G as a complete network, this is a symbol for complete network on N, it's always equal to S. For all S is a subset of N. No, this is for complete network. If we consider a complete network, for example, this is the complete network, right? With the 4 player, what we have the complete network. That, what do you mean by complete network? The every player is connected, right, with another player. So, okay, let me explain this then, that part. GN is a notation. I'm just saying that this is a complete network. G is anything, any graph. See, so total we have this graph, right? So G could be anything, any of these. But when, particularly when we consider the complete graph, so under the complete graph, it's not, it is actually not a partition. So S is not a partition. So here it is only a the whole coalition, right? I think in the next slide I have one example. So here I have a bigger example of a communication situation. So here N is, this is the 6 player set, and so for the 6 player set I can have this, right? So it will be like 2 to the power 15, right? So it will be 2 to the power 15 numbers of graph I can have. So among this graph, so this is the one a particular graph.
N over G is just the connected components of the graph.
N over, no, that's not component. I will come to that part later. That will become a component. But here I have a player set first. Over the player set, I am thinking as some graphs. Okay. This is not component. This is a one particular S, some coalition. This is also coalitions. So it makes the coalition into a partitions. I mean, it's divided the coalition into some partitions. So it's making the coalition in some partitions. Yeah. So, but here it is for the graph G, we have considered 2 components, 1, 2, 3 and 4, 5, 6. Right. So, here as I said, if we consider, so this is a one particular graph, right, among 2 to the power 15 numbers of graph. So, I can consider the complete graph also, Gn, the complete graph, right. I think that the first presentation I was using this notation, right, K15 like that. This notation I was using for complete graph, right, K15. Okay. If I consider the complete graph, so for any S over Gn, it will be S. I was mentioning that. So for here N over Z, so we have a 2 partition for the grand coalition. So whenever we are going to consider the complete network, we will not have any partition. Okay. So similarly, if I consider S is a one other coalition with 1, 2, 4, S over Z, it will be, say 1, 2, 4 in me, 1, 2 is connected. So that's why it belongs to the same coalition, and 4, it does not have any connection between 2 or 3, 1. That's why it's another coalition.
Can you do for 1, 3, 4?
Yes, 1, 3, 4, it will be what? 1, 3, 4, it will be like, okay. If I consider 1, 3, 4, it will be, so 1 and 3, they don't have direct link, but they are connected. So we need some connection among them. They should be belong to the same component. So then it will be 1, 3 and 4 is alone. If I consider say 1 and 5, if I consider say any coalition say 1 and 5, then it will be, they are, it belongs to different component. So it will be 5. Okay.
And S over Gn is equal to S. That's a part of the definition.
S over Z.
S over Gn is equal to S.
Yeah.
That's part of the definition.
No, that's not a part of the definition. I am just giving you as a special case. So part definition is this. This is how we define. So G and G could be anything, right? So G, we have this kind of graph. If I said this is the set of all possible graphs on N, or class of all possible graphs on G, so G belongs to this. Definitely Z N also belongs to Z. So this is a special case. You don't need to define it again. This is not a part of the definition. So this definition is enough. Okay.
Connected in S. It will be the set of S, right? Not S.
Set of S means?
I mean, it's a set of something.
Which one? Which one? You are talking about C.
S over G
S over Z, yes.
is a set of sets.
Yes, set of set. Yeah. Yeah. As I said, it's a partition of that set. Yeah.
So that would be singleton S, right? S over G to the right.
Singleton S, we can say this is a singleton S, right? Yeah. So we don't have a partition. As I said, we don't have partition. It's just the same S. Right. Yeah. Right. Set of S. Yes. Yeah. 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 Okay.
Again, connected in S means like, what do you mean by that?
I and J are connected in S by Z. That means they belongs to in the same component.
So when you take that 1, 3, 4, it will bring over to the next slide.
Yep.
You have 1, 3, 4. 1, 3 are connected via 2.
Yeah, yes.
in S.
So they belongs to, I mean,
But they are
yeah.
connected but not through all vertices in S. 2 is not in S at all. So what do you mean connected in S?
Connected in S means,
Just connected. Like, in this.
so you are asking me this definition.
Yeah.
I and J are connected in S by G. So said that,
ING connected by G makes sense. In S means you're looking only at the vertices of S or
yeah. Okay. So that means, yeah. So S, they are connected. Oh, yeah. Connected in G.
by
G by Z or, yeah, right. Yeah. Or we can say they both belong to the same component. Yeah, right? Only. Yeah. Okay, you have any question? Okay. As I said, we have if for a particular TU-GAM, we have for each graph, we have one communication situation. Okay. So next, okay, for each communication situation, we can define one associate cooperative game here. Right. So that cooperative game, as I said, so for this example, so we have so this is our Z, right, set of all, class of all graphs on N. So now I am considering only graph Z, this particular graph. So then I will have, this tuple is called the communication situation, and for this communication situation I will have a associate TU, or I can define a cooperative games, because this for S over Z is what? Actually again a set of coalitions. As you can see, these are actually what? Set of coalitions. Some class of, again, a coalitions. So on that S over Z, I can define again a cooperative game. So how we can define a cooperative game? So I defined a cooperative game as, so V any S is actually subset of these. So T belongs to S over Z this is the standard definition, but with this example, so let me explain how it is defined. Say, if I consider an, I think I should use the different notation, I guess. Okay, okay, let me use this different notation, and otherwise it will be a bit complicated. Say V over Z. V over Z, right? So here, my domain will be what? 2 to the power this, right? It will be a subset of n, or should I say it's all possible? Say for all S, we will have for a particular graph Z, for all S, I will have a different set of coalitions. Okay. So then you have to consider that domain. So as I said, it will be like S over Z for all S is a subset of N. So you will have this kind of domain. So can you imagine what will be the domain here? So for this particular graph, so we can have this kind of class of or collection of some coalitions for all S. So we have to consider that, or I can say it will be, yeah, or it will be, sorry? Yeah, it will be 2 to the power n, right. But there it will be like, okay, it will be 2 to the power n, sorry. Okay, there will be 2 to the power n, but in the other side it will be different. Okay, so then this is how we define the game. So for this particular example, here, so V over Z, and it will be what? V of 1, 2, 3, what of this coalition and plus this coalition. Simply the what of the coalition that makes partition over that G. And whenever we consider say 1, 2 and 4, it will be so S over Z, when S is 1 to 4, so we have the collection of the coalition 1, 2 and 4 alone. So we have this game 10. We have this what, then what for V over Z will be simply V of 1, 2 and V of 4. Okay. So this is how we can define a associate cooperative game for all possible graphs on N. Okay. So any question you have? No. Okay. So now Okay, from the TU game, n phi for each graph Z, I have a communication situation, right? For each communication situation, I can have a one associate cooperative game. Right? So now this is a cooperative game. Here we can introduce the all allocation rule here of, this is a cooperative game. We can introduce the allocation rule of the cooperative game. So what is the one allocation rule? We can consider the safely value. Right. So if we define the safely value for this game, so it will be like, so can you just try to find out the expression? So what would be like? It will be same, S is a subset of n minus I. The coefficient will be same, but it will be, yeah, V restricted to Z S union I minus B restricted to Z S. Okay. So if you express in this cooperative game V, if you apply this expression, then it will be what? It is sum over all coalitions. So it will be like, you can think about in this example, say I 1, if I consider I equal to 1.
Belongs to x restricted to z. So, like, isn't that just the sum of all elements? So, if you subtract vg s union I minus vg s union I, you get vg.
Yeah, it will be like, so when in which component I is connected, right? So one is belongs to this component. So we have to consider only this component. In the final expression, it will be here only. This component will be there. So are you getting my point? What I am trying to say?
We are applying the same formula, just restricted to the component in which that particular element is.
Right, right. So if my G is this, right? So we can only consider only this component. So we don't need to consider this component while we are calculating the safely value for that associate cooperative game.
Can you give the reason again?
Because of this is additive, right? Simply summation over that. Okay, okay, just let me erase this part.
Okay, it will cancel out. Okay.
Yeah, it will cancel out, right? It will cancel out. Yeah.
So, only the second bracket will be just one term.
Yeah, one time. Because here it will be like, so we will have a, okay, just simply do one thing. So for the only the grand coalitions, you can calculate it, right? So V over G and minus V over Z, it will be how many players are there? 2, 3, 4, 5, 6, right? So you can do this calculation, right? Over Z. So it will be like, this is actually what? V of 1, 2, 3 plus V of 4, 5, 6. Here it will be minus V of 2, 3 minus V of 4, 5, 6. So it will cancel out, right? So only we are going to consider the marginal contribution where the player I belong to that component, right? Yeah. So that's how it, after that component additivity value function, the concept of component additive value function comes. Okay. So I don't want to discuss that concept in a communication situation. I just want to show you. So these are also, I will discuss this theorem. This is the same kind of theorem that was extended to network games. So next I have one example here, and this is a 3-player game. So I have a total 8 number of networks, all possible networks, all the Shapley values are associated, we defined this is the cooperative game, TU games, right? So then we have some associate cooperative game for all possible Z. So then I calculated all the Shapley value for the all communication situations. So when we define the communication situation, the Shapley value itself we call is a Myerson value, because the value was extended to the communication situation by Myerson. So later on it is renamed as a Myerson value. Okay. So definitely for the empty network it's 0, 0, 0, and if there is only link between 1 and 2, 3 is isolated, so then we can have the Myerson value as a 6, 6, 0. Okay, 1 and 2 they are getting 6 and 6, otherwise 0. But this Myerson value is efficient. Okay. So how the Myerson value is efficient? This is simply equal to the worth of the coalition generated by player 1 and 2, right? So if the network structure, I consider the network structure is like that, 2 and 3 and empty, right? So then it will, 1 definitely is the isolated link, he does not have the link to any other, so Myerson allocates him 0, and 2 and 3 will get 3 and 3. Okay. So definition of the Myerson value is, as I said, we define that, where I define that Shapley value for the associate cooperative game. The associate cooperative game we define this way. And this is the Myerson value, this actually what is the Shapley value for the associate cooperative game. The Shapley operator, as I said. Okay. So we have a network, we have a cooperative game here, and on the network cooperative game, we just introduce the idea of graphs. Okay. When we introduce the idea of, the graphs in the network cooperative game, then we have a set of communication situations, and for each graph, we can have a Myerson value, right? Okay, and this Myerson value is efficient, you can see, right? Yeah, sure. Okay, I will introduce the concept of component balance and equal bargaining power in network games. Okay, because I don't want to talk about communication situation, because there are lots of drawbacks in communication situation that I will come later. Next I am going to discuss about what is the criticisms about that communication situation. Okay. Okay. So another thing I want to say, when we consider, this is the complete graph, right? When I consider the complete graph as a communication situation, this is simply actually the Shapley value for that TU game. Only for complete graph, only for complete graph it is equal. This is for complete graph, and this is the Shapley value for this TU game. This is a TU game, right? Cooperative game. Then definitely we can have a complete Shapley value here, and Shapley value for this game is actually what? 552. These are also safely value. These are also safely value, but this safely value, this is equal to this TU game. Right. Any question you have till now?
I didn't understand the last part. All are shaped in
See what I said.
Okay, so these are different graphs.
Different graphs. For the different graphs, you can have a one associate cooperative game. On that associate cooperative game, you definitely can define a safely value, right? Yeah. So we have a 8 numbers of graph, including empty graph, right? Any more question you have? Okay. Okay. So what are the criticism of cooperative games? So first criticism was that, so whenever we consider the network structure, say if I have a one Q game and V, if I consider the network structure, say N is the 3-player game, right? So we have a two different network structure. One is complete and another is only 1, 2 is connected, 2, 3 is connected, and 1 and 3 is connected through 2, but they don't have any direct connection, right? So, but under communication situation, what happened? We consider that the coalition can generate what? When they have some connection. They have only some connection, but it does not say that how they are connected. The network structure does not, if their network structure is still different, then we will have a same allocation, same what? Yeah, right. So there is a one condition. The question is that, is this value should equal?
Our model will tell us that it's equal, but the connection.
But in real life, do you think that the connection, if 1 and 2, 3 directly not connected, or in this another graph they are directly connected? So do you think that in real life that this kind of situation, it should happen?
It depends on what we are modeling, right? Because in some cases, one can actually transfer information through 2 to 3, and in some cases, there will be some loss of information.
Yeah, we have some examples or some situation there, it should not be equal. So,
The more number of distance you are traveling, the more loss it is. At each part, at each age, you lost some information.
so do you have any example? Like,
Information transmission, like
huh?
you transfer from 1 to 3 directly,
Oh.
you have minimum loss.
Yes.
If you go through like 5 other vertices and come back to 3, then you have more loss. Because as you travel a lot of distance, you lost information.
Okay. So, I have another example, that is biaxial model. So, that's a little bit different.
Number of mediators you lost.
Yeah. If there is a one mediator between 1 and 3, see 1 is a say buyer. If I say this is another, this is a seller, this is a one buyer, or say this is a buyer, I can say, or say mediator, right? So then definitely whatever the what they can generate together in this network, the profit for the seller is less. If they have a direct connection, then he will get more, the profit will be more. So network structure should, if we say that the network structure should matters in that generating the coalition, what of that coalition. So then it is the definition. Okay, so then that Jackson and Ulinsky, so this is the article actually, Ulinsky first introduced the idea of the network games. So in a network games, what we have a player and somehow they are connected. There is some network connection among these players, and the value that we define it depend on the network structure, how these players are connected. So in this particular example, so for a network games, the network structure is different. Okay. So together with this pair N and V, we call the network games. So what is V? What is the domain of the V? So domain of the V is the Z. It's a real value function. What is the Z that I already defined? Is the class of all possible networks on N. Only such that the empty network will generate 0 worth. Okay. Okay, before that I just want to mention some notations here. These are some notations. We already discussed in the first lecture that if there are two networks Z and G plus, and when we are think about the adding this network, we are going to use this notation G plus Z minus G prime, and if we want to delete, so suppose this is a one network J, right, and I want to delete some part, this part, if I want to delete, so then I just simply mention it is this G minus G set minus G prime, like that way, deleting some network. Okay, and this L and Z is actually the set of all links in G, and the cardinality of LG, the set of all links in G is simply the small LG. Okay. And what is the NG? The numbers of play or the set of all players in G. Okay. L small iz is the set of all the links. Yes, from I. That means the you can say the neighborhood of I. Yeah, this is actually one neighborhood of I. G over S. Do you remember spanning an induced subgraph? So this is actually induced subgraph. Right. So what? Okay. Small Liz is the numbers of links. It's a neighborhood of G, right? So it's the cardinality of this set. Okay. Right. So we are going to use all this notation to define that allocation rule in the networks. Right. So now component, you know. Yes. The last part you are talking about this part? Which one? You are talking about this part? Notation is what?
So that's nothing but edges, the links from
All the, yeah, we are going to consider all the edges actually, yes. Actually this is the neighbor players, I mean all the neighbors, links with all its neighbor players, yeah. No, it's not a degree. The numbers of links in the player I said is, yeah, correct, Or you can say that cardinality of the neighborhood of I. Degree, yes, degree, yeah.
and G bar G prime is just links deletion. You don't delete the nodes. G slash G prime.
G slash G prime is actually removing or deleting some
Links.
sub graph from G. Yeah, deleting some link, removing some links.
You don't delete the.
It could be a one link or it could be a subgraph. So in this case, I am saying the G prime is what? This two subgraph of G.
What's the remaining? What's the result in G minus G prime in this case? In that example.
This is my whole G.
Ah.
Okay, just let me erase this part. If I say this is my whole G, I am considering, so let me label it. So my G prime is 1, 2, 2, 3. So I want to delete the link 1, 2 and 2, 3 from G.
But you will retain that 1 and 2 as isolated nodes.
So here is one not isolated. I am just saying from this network I want to delete them.
Yeah.
Just want to delete them. So it will be what? It will be simply 4, 5, 6, 3, 4.
There is set difference.
Yeah. So it will be like only this network.
Oh, you don't have 1 and 2
No,
now.
no, because I deleted them.
Oh, that's what I said. So you don't delete only the links, you delete also the nodes.
Yes, everything. Yeah, the subgraph. As I said, the subgraph. So 1, 2, 2, 3, those are subgraph. Okay. So we don't have isolated link here or isolated node.
3 is also deleted, right?
Hmm?
3 is also deleted, right?
No, 3 is not deleted. I am the deleting 2 and 3, link 2 and 3. This link and this link.
But now 1 and 2 should be different components.
1 and 2, I think, no. Thing is that I am going to consider only this network, sub-network. So from the network, deleting this part means 1 and 2 is not there. See, if in this network, say there is a 6, 7 is there, right? So then it will be 2, 7, then it become another component.
But 1 is not there.
1 is not there, or I can say 1 is an isolated player. So it does not matter actually 1 is an isolated player or not, because he can't generate any word. No, not the nullifying player, it's a isolated. It's not interacting anything. See, in a network games, when I say the network games means they can only generate word if they have some link. Otherwise, they can't generate anything. So we don't consider that isolated players in networks. So we consider that automatically their word is 0. They are generating 0, definitely every allocation they should get 0. Okay. Any more question you have? Okay, so next definition is the component of a network Z, and you know what is the component already, the maximally connected, right? So, okay, so let me introduce one thing here, component additive value function. So I define, as I said, if N is the player set, we said G is the set of all possible networks on G, then we define a value function on G, a real value function with the condition that empty network will generate 0. So as I said, when I said that the empty network, we can have some isolated node, right? Yeah. Okay, so next talk about the component additive value function. So as you know, what is the component? Say for example, this is a one network, it has these two components, right? So Z1 and G2. I am saying that this is a one component G1, this is another component G2. Let's take another one more component, this is G3. And the whole network I am saying is G. Right? So how many players I have? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 players. So component additivity means what? The V of Z is actually equal to V of G1 plus V of G2 plus V of Z3. That the total value that is generated by whole network is equal to sum over all the word that is generated by each component. Right? So let me write here the general definition here. It's a component of Z. CZ is what? The set of all components of J. So here we have a 3 components G1, G2 and G3. Right? So in a network games, we have a 2 different kind of value function. One is component additive and one is not component additive. Okay. So we mostly talk about component additive value function. Right? So this definition is clear. Alright. Okay. This is a definition for component additive function. So as you remember about that yesterday we talked about that the set of all or the class of all cooperative games on the player set N, it's a linear space. And we talked about unity game, that's the basis, and the dimension is what? 2 to the power n minus 1. So here we have a same kind of result. The set of all network games on G, it's again a linear space and these are its bases. This is almost similar to the unity basis. So now my question is that, so what is the dimension for this linear space? Both component additive and if the value function is not component additive. In both cases, what do you think? What would be the, for n is fixed, right? So how many, what is the possible number of graphs we can have on n? 2 to the power n is 2 minus 1.
So that is the total number of graphs. But
what is the domain here? Z, right? How we define V? V is a function for
all the networks. So if we have
oh sorry, this is only V. Either V is component additive or not component additive. Huh. So V is the class of all value function on G. And I say V either is component additive or non-component additive. And let me define another definition. So V of CA is the class of all component additive value function on G. Now as I say, the V is a linear space. Both V of CA or V, they both are linear space. And in both cases, these 3 are their bases. Now what do you think? What is the dimension? It's simply 2 to the power
number of links in that component.
what?
Like if, for example, G has, as we defined earlier, L of G is the number of links in G, then
Now what is Z here? I am saying Z is the all possible networks or graphs on N. No, I am not saying that G is fixed. Yeah, right? So dimension for this graph it will be what? 2 to the power and C2 minus 1. We just simply remove that empty. This is the dimension. Right? Okay. So then what? Anything else here? Okay, this definition, the associate cooperative definition, game definition is not necessary. We can always, once we have a network game, we can construct associate cooperative games. But in for the Mayasian value, this is not important that much. But if we have a player link based allocation link, that it is important. So I will discuss that different kind of associate cooperative game later. So before that, let me talk about what is a link based and player based allocation rule. Okay. So now I have the network game. So I have a given network structure, and on the network structure, say G network structure is there, right? So on, yeah, sure. Here, yeah, three functions. Yeah, each of them we have basis. So this is actually unity. So yesterday we talked about this only. This is also one kind of. This is also another kind of. Which one is a subgraph? Yeah, subgraph, correct, subgraph. Yeah. So yesterday, what is the definition I gave you for unity game? Do you remember? It's just an extension from there. So S is a S contained in T, otherwise 0, right? So here, the same definition, unity. So if it is 1, if Z contained in that graph, suppose this is my graph. So let's take in one example. So this is a one graph Z, right? Or Z prime. So one Z prime could be what? This can be a one Z prime, Z, right? Could be anything. So for all subgraph of Z prime, it's 1, otherwise it is 0. So otherwise 0 means if this is a say this is not in G prime, this is my Z prime, this is not in G prime. If I consider, say suppose this part, this link and this link, then it will give 0. This is not a subgraph of G prime. Okay.
Why did we define it like 3 and 4? The information in 3 and 4 is already conveyed by 2, right?
No, I am just saying that this, we can have a 3 different kind of basis. So yesterday also I discussed only one kind of basis. So in cooperative game also we can have these 3 kind of basis. So these are 3 different bases that can generate whole the vector space. Yeah. Any more question you have?
Do the component additive games from vector surface?
No. It comes from the graph structure. Okay. So once I have the network games, right? Once I have the network structure G, on the network G, I can define a network games or the value that on the subgraph of Z, right? So then the question, once the game is defined, the what are generated, among the subgraph of Z. So then the question is that how we are going to allocate the worth of whole Z among the players. So Z is any network. I define a network. So N is the player set, right? So Z is any network on N, players N. So V is the value function, the words are generated among the subgraphs of the Z. Now the question is how we are going to define the word that VZ among the players in I, where the player belongs in I. So that's the question. So the first, how we can define, how we can allocate. So we can allocate first directly to the players, right? And then another way we can allocate. So first, so in a network we have two components like players, nodes and edges. So first as a player base, each first we allocate the nodes. So other way what we can do, we can allocate the nodes also. What we can consider that in a network, say this edges, say I, J, K, L. For this particular network, I can consider that the link I, J, I, K, K, L. There are 4 links among I, J, K, L, right? So these are hypothetical players that we can consider.
We are considering the edges as players.
Yeah, hypothetical players, right? We can consider that.
Instead of allocating value to the node, we are allocating value to the edges. So that is how we can get the dependencies on the structure of the network.
Right, right. And then we can say, so eventually we have to allocate the players, right? So once we allocate the links, what we can do, the allocation of the links between the player I and J, that we can divide equally. That's a fair way we can divide equally. So we are considering that they have equal contribution. In some cases, suppose that if we say that they don't have equal contribution, and we can we can do that. So here we are considering, first we are considering that they have equal contribution, so that's why it's a equal division.
For example, if we have provided the value to the edges in this small graph, then value of I will be half value of ik plus half value of
Yes, correct. So for I, if I say it will be half of whatever the allocation it will get from Ij plus half of the allocation from Ik, like that. Like that.
So how do you divide that to edges? You have 3 edges here. Then divide by 3.
3 edges is something is 3 edges, yeah, divided by 3. If I have another link, then it will be again, he will get, yeah.
I was asking how do you divide? How do you allocate to edges? From edges you allocate half.
That we will going to discuss. Just I am saying that these are 2 possible way we can think about the allocation rule. Then we are going to think about that some particular in special like Shapley value, Myerson value we can think about. I am just saying this is a 2 process. Then we are going to discuss that. This is some special kind of cohort models that here I just wanted to show that value function, how the value function is defined here. So this in this paper, so I am just discussing this paper, mostly Jackson and Ulanski 1996. So the networkgram started from here. If you want, I can share this paper to you. If anybody interested, just let me know. So then is another paper by Jackson only, published in 2005. So these are the main articles for network games. Okay. So here what is the agent players are there considering that some researcher. So it's almost like collaboration network, like that is researcher, they are working in a project, they can work alone also, or they can work with somebody also. If someone has a one, say I has a link with some another player agent J, that means they are working together in a project, one project, like that we can think about it. And that value is defined as a, say 1 by ni means for the particular player I, he how many projects he can have, and it will be proportionally divided, I mean it is divided by, so his total time is say considered as a 1, or I can say 1 is the whole day or 24 hours, and it is divided, equally divided, the spending on time, say each project he is spending 1 by n minus I times. Suppose somebody has a 2 project, and for the whole day he is equally spending some times, some particular times, say for 2 hours or 2 hours, like that.